in this video we're going to be solving differential equations that have a very particular form, this kind of composition of functions form, using a substitution technique. And I'll be honest, this is a technique I was not familiar with up until recently, because it's not in the Boyce and DePrima book. So, but it's something that we could definitely solve, and it may be something that you would see in kind of an introductory differential equations course. So let me show you really what we're going to be interested in today is going to be y prime is some kind of f of g of t and y. And it seems to me, based on the examples of this that I've seen, that this interior function g of t and y pretty much needs to be linear in t and y in order for this to really have a good chance of working. But the first one, I think I just want to work the example and show you how it works, because this is not something that I can just solve in general for you. So the first one I want to talk about is y prime is 4t plus y squared. Okay. Now, this is the type of thing. This is a first order differential equation, right? All we see is y prime. But it's not going to be linear, because we're going to have a y squared, and we're going to have t, no, actually, no, that would not be a problem. It's the y squared that makes it not linear. But if we consider what happens when we let v equal 4t plus y, we'll see that this can become a separable differential equation, and that would be nice. So what I'm going to do is I'm going to say let v equal 4t plus y. And I think that, maybe I'll show you. Where are we at now? Well, here we would have y prime equals v squared. Okay. Well, y is a function of t, and v is also a function of t, but that's not going to be good enough for us. We need to get an expression for y prime in terms of v and t. But that shouldn't be too hard, because I could solve for y here and then take the derivative implicitly with respect to t. Okay. At this point, I probably should remind you that, if we're looking for a solution to this equation, it's going to be some function, right? Y equals some function of t, hopefully. So y is a function of t. 4t is a function of t, meaning v is also a function of t. So I'm going to actually just write that. So it'll make it a little more obvious when I go to take the derivative of y with respect to t to get an expression for y prime that I can substitute there. Okay, so in this case, y of t is going to be equal to v of t minus 4t. Okay, so the derivative of y with respect to t, that's y prime, is going to be the derivative of v with respect to t, v prime, minus the derivative of 4t with respect to t, which is going to be 4. And now this is something that we can really substitute on, right? Because if y prime is equal to this, and it's equal to that, okay, well, I can just say that v prime minus 4 is going to be equal to what we're now calling v squared. So I'm going to say v prime minus 4 is equal to v squared. Okay, then I'm going to add 4 to both sides of this. V prime equals v squared plus 4. This is separable, okay? This is also an autonomous differential equation, right? It's only in terms of the dependent variable, just to talk about a video I had a couple times ago, but this is not gonna have any equilibrium solutions, right? Or at least any real ones. Okay, so I'm gonna come up here and start to do my separation of variables. So dv dt equals v squared plus 4. Meaning 1 over v squared plus 4 dv is equal to dt. Okay. And, okay, I'm going to need to anti-differentiate both sides. And this one, that'll be easy, that'll be t plus c. 1 over v squared plus 4, though, well, I'm trying to decide how much detail do I want to get into here. This is going to be, I'll just tell you what it is, and then I will kind of describe my methodology here. This is going to be 1/2 of inverse tangent of 1/2 x. V, pardon me. Okay, and how I arrived at that yesterday in class was, let me grab a color. So I would start, okay, 1 over 1 plus x squared is the derivative of arctangent of x. So, I don't know, for me, my personal thought would be, I might think of arctangent of 2v first. And so, I would just say maybe arctangent of 2v, I take the derivative, and I'm going to get 1 over 1 plus 2v squared is going to be 4v squared. And then I'm going to multiply by 2, so this just seems wrong, right? I need 4 plus v squared, not 1 plus 4v squared. Okay, so I'm going to be like, this isn't going right. So maybe I'll switch it to arctangent of 1/2 v and see what happens. Okay, so if I change that to a 1/2, I think I feel a little better because this will become a 1/4 of v squared. And at least my ratio is right? I'm also going to have to multiply by 1/2. So yeah, I'll just do that. And if I was to take this thing on the left and multiply it by 4 over 4, right? I'd just be multiplying by 1. I wouldn't be changing the thing. I'd be having 4 over 4 plus 1v squared. So I'm really close, right? Because once I divide that 4 by 2, what I really have is a 2 in the numerator. And so to prepare for that, to get 1 over 4 plus v squared, I'm going to multiply that by 1/2. Okay? I'm sure there's a better algebraic substitution technique, but this is one of those complete the square integrals that, it doesn't come up often enough for me to memorize the technique, and I ain't just always going to feel my way through it. So I've got 1/2 of arctangent of 1/2 v is equal to t plus c. And now I'm going to start solving at v, because if I get v on its own, I'll be able to get y on its own, because I've got a formula for y in terms of v and t. So I'm going to multiply both sides by 2, and so I'll have arctangent of 1/2 v equaling 2t plus c. And then I'll take tangent of both sides. Okay, so 1/2 v is going to be tangent of that, so v will equal 2 times the tangent of 2t plus c. And then I know that v is 4t plus y. And then I can solve at y, and I can get my general solution. Y of t equals negative 4t plus 2 of those tangents. Okay. And this is a pretty solid example of that substitution technique that I'm talking about on a composition of functions for your differential equation. Just while I'm at it, I might also mention a couple more examples that, would fit this pattern, just in case, you were looking at a set of practice problems and you didn't know which technique to use with which one, right? Another kind of composition that would fit this mold. So other examples. Other examples could include 1 over t plus y. So y prime equals 1 over t plus y. Also maybe like inside a square root. So square root of, maybe t plus y plus 1. Those are the two I have just, off the top of my head. I'm sure there are others, but, these two might be ones that you find yourself encountered with here pretty soon. All right, so that's all I got for you for this very specialized case.